Today, we are going to continue at the last deformation. Last deformation, we assume that the material has the ability to retain its shape, original shape, after the removal of a force. But this is because most of the structures sustain the loading. So this the reason why it's very important time in the elastic deformation because due to that. Because when you apply a structure onto a soil, you do not take away that structure. So it elastically go through that immediate settlement or immediate deformation, which is elastic in nature, which is the deformation due to the movement or due to the compression of soil. Is that okay? Due to the compression of soil or due to the reduction or the change in shape of the soil or of soil or soil particles. So normally, if you remember that from our expression, how do we move from this to that? The stress and strains for linear isotropic elastic soil are related through Hooke's law, and this is what we call the constitutive equation or model. Is that okay? A model which relates strains to stress. Is that okay? Because strains are a result of stress. So how do we come up to this? Let us take an example of this stress. Okay? Let us take an example to this stress. So here we have what called the strain, the axial strain. Here we have what called the shear strain. Is that okay? The shear strains. So the shear strain, they are related with what called the related with bulk shear strain. Remember, this is equal to the shear stress divided by the what we call the bulk modulus. So the shear modulus. This is what called the shear G. The shear modulus. Is that okay? So in that the relationship of shear modulus, this comes in. So we can have that the shear strain from this relationship here. We can be able to obtain the equation which relates the shear strain to the shear stress. Is that okay? To the shear stress. That said, I can remove this. Come back to our original formula. So that said, let me take this for instance this. So if I can get my pencil back. So remember the strain. Let me try to use here. My pencil strain. Forgive my in Z. Is equal to stress. Stress is equal to stress in Z divided by the Young's modulus. Is that okay? But when you apply a stress in Y, it will cause also a deformation in what? An expansive deformation in the Z direction. Is that okay? Now, if you remember our Poisson ratio, which was saying that a Poisson ratio is equal to the negative of stress of strain in X divided by strain deformation. Sorry, strain. A minute. You can go back. Go back to this. We are saying that is equal to, if I go back to my pencil, if I go to hope it will work well. And so that we say that this Poisson ratio, if I can use this place here, simply explain a little bit here, is equal to negative. Or for instance, you're applying the stress here, which causes a deformation here. Remember, when this one moves inside, this one will move outside. Okay, it bulges. When you apply, it bulges. It bulges. You only push here, and this one moves out. Is that okay? It moves out like this. So now, if this is fixed, now it will just move out like that. Is that okay? Now, for what's that strain here? These two strains, that's the result of application of a force in this plane, and the strain which occurs, the deformation which occurs in Z is related by what we call the deformation, what we call the Poisson ratio. Is that okay? The Poisson ratio. So is equal to, now for the lateral strain in Z divided by, this is Z, sorry, in Z divided by the strain in X. Is that okay? Therefore, the strain in Z, as a result of application of a force in X is equal to, can go here, the strain in Z is equal to negative V times, remember this is our Z here, Z times the strain in what? The strain in X. Is that okay? That's the strain in X. So now you substitute for strain in X. The strain in X is equal to now this one will be equal to, again, if you can expand it, to negative V into stress in what? Stress in X divided by Young's modulus. This one is equal to the strain in what? In Z, as a result of applying a stress in what? In X. And also when you apply a stress in Y, still there will be a deformation in what? In Z. Therefore, so strain in Z is equal to negative V as a result of applying a stress in Y divided by Young's modulus. Is that okay? There will be a deformation. Now for the total strain due to the application of this system of stresses in Z is equal to this. This is Z, stress in Z divided by E minus. Remember, this one will tend to go up, but there will be a subtraction, a pushing strain as a result of this, and as a result of which, therefore, say now minus. There will be a reduction. Is that okay? A reduction in this strain as a result of this, minus again as a result of this, which will give you such a line of what? When you, for instance, if you invert, now for this this one here is equal to what exactly do you see here? Okay. So this one here, I meant this. This is in Z. I can remove this. Remove this. Remove this. And remove this. So now for the strain in Z is equal to this negative plus this divided by E. Is that okay? That's how you come up with this. With this constitutive model. Is that okay? So you can predict all the strains in X, Y, and Z deformation as a result of applying the stresses, these stresses in Z, Y, and X. But if, for instance, if these are principal stresses, these are principal stresses, now for the shear stress is 0. This the bottom part is 0. So now we got to call the principal stress. The principal stress constitutive what? Constitutive model, which is this one here. Now for when these are zeros, so when you take this to be zeros, starting from here, this if this one over this one, all these ones go off. Is that okay? So you get a 3 by 3. For principal stress, remember principal stress, the shear stress is equal to 0. Now this is the major model we'll be using. Is that which comes from that side when I assume that principal stress is equal to 0. Okay? When the principal stress is equal to 0. Is that okay? Therefore, when you apply this is if you apply a major principal stress, a minor principal stress and intermediate principal. Now for the minor, the major and intermediate, then you exactly get such elastic principal strains. You get what called this principal deformation. Is that okay? You get what called this principal deformation. So how do we get, now for the total deformation, will be equal to the total sum. Remember, this is summation. This is a summation. Is that okay? Or it will be very simple. You get in Z, in one direction in Z, you just get, remember, deformation. If we go back, remember this is what when you get the total deformation. Remember, change in Z, change in Z divided by Z, the original length, is equal to strain in what? Strain in Z. Therefore, to get the total deformation, this is Z. Now, to get the total deformation, we just get Z, the total strain times the original length. Is that okay? So now for the deformation, total deformation is equal to Z times the strain, which has what? Which has the strain in what? The strain in Z. Is that okay? Which is this equation here. Now, for still remember, I know that force is equal to the applied stress times what? Times area. Force times area. So that you can as a result, okay, the force in the member as a result of application of a force, the force increase. These are increases. Is that okay? These are increases. So we have, these are principal stress. Now, let us go to the application. How do you apply in engineering? Basically, you apply in two cases, two conditions. The first condition, what we call the plane strain condition. The plane strain, it occurs when we assume that the deformation in Y, when you apply a force and there's a retaining wall and there is a soil, or there's a vehicle moving and there's a stress increase at this point. Is that okay? Now, if we want to get the deformation behind the wall of what? Of a retaining wall, how the soil will move behind the wall of this. Now, this is what we call the plane strain. There are two conditions of stresses and strain that are common in geotechnical engineering. One is the plane strain condition.